eTraining course Discovery DSC Data Analysis using TRIOS. My name is Kadeen Mohammed and I am one of the many application scientists at TA Instruments who can help you become proficient in the operation of your new Discovery DSC. In this course, we will cover topics which include opening the DSC data file in TRIOS, reviewing the parameters and graph properties, analyzing transitions, overlaying multiple plots, and exporting plots to spreadsheets and external programs such as PowerPoint and PDF. At the end of this course, you will have the tools necessary to analyze and report your DSC data files. If you should have any questions regarding the Discovery DSC, TRIOS, or DSC applications, please do not hesitate to contact us at the Thermal Support Hotline by telephone or email. Let us begin by opening the TRIOS software through the TRIOS Bubble or the TRIOS Instrument Explorer. When selecting the TRIOS Bubble or Explorer, you will find a list of instruments connected. Here we can see that I am launching the software while not connected to the instrument. This allows for offline analysis of data files on a computer that is not tied to the instrument, such as your office desktop. You can also connect to an instrument that is online and analyze DSC data as the instrument performs a sequence of experiments. As TRIOS is launched, you will note that it defaults to the experiment's design view. For data analysis, please select the Results tab located in the lower left corner of the window. From here, you will now be presented with the File Manager window. The File Manager window allows you to open TRIOS data files as well as Universal Analysis Q-Series data files within TRIOS. This window can be hidden from view, closed, and then reloaded as needed. To open a data file, select the Open File icon. To find a data file, browse to the location or directory where you have saved your data files. This can be a network folder, a local folder, or a removable USB flash drive. Here we have a data file that has been opened in TRIOS. In this section, we will review the data file information and parameters along with editing the graph properties. Let's look at the Run tab located in the lower left-hand corner of the window. The Run tab contains information that was input when setting up the experiment in the design view or the running queue. This includes sample name, sample size, auto-sampler tray position, and procedure. The next tab is the spreadsheet view of the selected step. This data file has one step or cycle, but multiple steps can be viewed individually as needed. You can copy the columns from this spreadsheet view into spreadsheet programs such as Microsoft Excel. The data can also be exported by selecting the file in the File Manager window, right-click, and then select Export, and then select to Excel to send to a spreadsheet program. The third tab is the Graph tab, and it displays the plot. You may choose to rescale the plot by selecting the toolbar icon Manual Rescale, or right-click on the background of the plot and select Manual Rescale. Let's look at editing the scale on X-axis where we're looking at temperature. To edit the temperature scale, select Scaling and then Manual, and input the range of interest. You may also choose to edit the tick marks by selecting Use Intervals and entering the values of interest. Select OK. And the file has now been updated. You may choose to reposition the plot by using the scroll bar that is located next to the label axes. And you can always go back to full scale by selecting the full scale all axis icon or by right-clicking and selecting full scale all axes. On the plot, you can display the title, header, as well as legend. Both the title and legend can be edited. You can also annotate the plot as shown here. Another tab of interest is the Parameters tab. Right-click on the file in the File Manager window and then select Show Parameters. Within this window, you will find greater detail regarding the data file information as well as the calibration log. Let's move on to editing graph properties such as line color, font size, and graphical displays. Right-click on the plot and select Properties. In this window, you will find a pull-down list of what can be edited. Let's select Axis X1. Here we can see that the variable being displayed is temperature, but I can choose any one of the signals that have been saved to this data file. The next is the units. I'm currently displaying on a degrees Celsius scale. I can edit this to degrees Fahrenheit and it will automatically update the plot and scale. Further editorial changes can be made to the font and font size, as well as the colors used within the plot. These changes are updated immediately on the plot and can be saved as a default setting if desired. The process of curve shifting and curve rotation causes a linear change to a curve's baseline. To get to the shift and rotate options, select Analysis from the menu bar and then select the Shift Rotate icon located on the toolbar. Located to the right is the icon for the Shift option. Curve shifting moves all the data points up or down by a fixed value. Curve rotation, located here to the left, moves the data points on a curve up or down by a linearly changing value. When rotating a curve that will be subsequently integrated, be sure to rotate the curve using the same x-axis domain as the integration, and this is typically on a time domain. Rotating a curve in the temperature domain and then integrating with respect to time can result in incorrect integration values, because typically time and temperature are not linearly related as a material goes through a transition. In general, you should not rotate a curve in the temperature domain if you plan to integrate a peak within that plot. If you are satisfied with the changes impacted by the Shift and Rotate options, select the Accept command on the toolbar. Multiple data files can be opened and analyzed within TRIOS. To do this, select the File Open icon and open the data files of interest. Note that the DSC Cure data file is a thermal data file that has been generated on either 2900 series DSC or a Q series DSC, and these data files are typically analyzed within Universal Analysis. These files can be opened within TRIOS and can also be saved as a TRIOS format data file with a TRI extension. To create an overlay document, highlight the three data files, right-click, and then select Send to New Graph. Note that a File Overlay tab has been created. To edit the way in which these data files or graphs have been displayed, select Curves, and under the Mode, select Custom. Here we can edit the colors, symbols, and line styles, as well as the symbol density. To further enact changes, select Scheme, Customize Current Scheme, and then edit the colors, symbols, and line styles as desired. For instructions on creating further overlay documents and saving overlay documents, select View, Help, and from the Help topics, select Analyzing Data and then Creating Overlay Plots, where you will find a wealth of information regarding how to create overlay plots with multiple cycles as well as how to save the data file. Let's now move on to analyzing a DSC data file to determine the heat of reaction, heat of transition, typically known as the enthalpy. To do this, I've opened an indium data file which has been run using the following test method. Equilibrate to 180 degrees Celsius, equilibrate to 100 degrees Celsius, and then ramp 10 degrees C per minute to 180 degrees Celsius. The first two steps are used to pre-melt or precondition the indium sample so that it has ideal thermal contact with the bottom of the pan. And then data is collected during the ramp segment, in which we heat from 100 degrees Celsius to 180 degrees Celsius and determine the onset, melt peak, as well as the enthalpy. Going back to the plot, I'm going to rescale this plot so that I can zoom into the temperature range of interest. To perform a peak integration, you have two options. You can highlight the temperature range using your cursor, right-click, select Analyze, and then Peak Integration / Enthalpy. Or you can select Analysis from the menu bar, and then from the pull-down list, select Peak Integration. Within this window, you have the option to select Settings. Within Settings, the Pre-Start Status allows you to determine the baseline type used for the analysis. Because the slope before and after this particular peak is on the same value, then a linear baseline is used. However, if the slope of the baseline had changed before and after the peak, then you would use a sigmoidal baseline. Select Set Limits, in which you now have two crosshairs in which you can define the temperature range for your analysis. You can also, now under the status of selecting limits, manually type in the temperature range that you would like to use. Right-click on the plot and then select Accept Limits. What's being displayed is the onset temperature, enthalpy, and peak maximum. Now, if you're not happy with the temperature range used for the analysis, you can adjust these limits on the fly by selecting Adjust Limits and then manually adjusting the temperature range of analysis. And note that the enthalpy as well as the onset temperature will be updated with these changes. Right-click, select Finish Adjusting, or select Finish Adjust from the menu bar. Let's now open a DSC data file that uses a sigmoidal baseline when performing the peak integration. To do this, select from the File Manager the File Open icon and browse to your DSC data file. Here we have a thermoset material that has been cured in the DSC using a standard temperature ramp, and the data is being displayed between 50 and 200 degrees Celsius. Note that the baseline before and after the peak is not on the same slope. As a result, when performing an analysis, you will need to change the baseline integration selection from linear to sigmoidal. To do this, you can either highlight the temperature range that you would like to analyze, right-click, select Analyze Peak Integration, or from the menu bar, select Peak Integration, Settings, and under Settings and the Pre-Start Status, change your baseline type from linear to sigmoidal. You also have the option to use for the left and right limits of your cursor analysis, horizontal, tangent, or manual tangent. For further information regarding these options, select View, Help. From the Help topics, select Analyzing Data, Available Analysis Functions, and then Peak Integration. Within this window, you will find information defining a linear baseline, horizontal baseline, sigmoidal baseline, as well as the limits used for horizontal, tangent, and manual tangent, and the differences between the three options. With this particular analysis, I would also like to display or demonstrate how to perform a partial area analysis. And to do this, select Divide Peak. By selecting Divide Peak, you have several more options. The type can be Divide Peak into equal X regions, fixed X intervals, specific X temperature value, or at peak. I'm going to select specific X and type in a specific temperature value of 100 degrees Celsius. Now select Analysis, Set Limits, and define the temperature range for the analysis by adjusting the two crosshairs. You can also manually input these values. Right-click on the plot and select Accept Limits. Let's look at what is currently being displayed. The onset temperature for the peak analysis, the peak temperature, as well as the total area or enthalpy for this Cure reaction. There is a perpendicular drop at 100 degrees Celsius, and the partial area analysis prior to 100 degrees has been performed and is being reported here as 18.42 joules per gram and a partial area analysis of 7%. The next area being analyzed and displayed is the area after 100 degrees Celsius, which is approximately 92.97%, and the enthalpy, or heat of reaction, is 243 joules per gram. If you would like to adjust the limits of your perpendicular drop, you have the option to do so by selecting Adjust Drops. Under Settings, you can also decide to edit what is being displayed within the plot. You can choose to display the type of analysis, in which here we have here peak integration, enthalpy, as well as under Appearance, you can choose whether or not you would like to have your analysis or annotations match the color of the curve, whether or not you would like to use black for labels, as well as to suppress the label names and use just numerical values. You can also choose whether or not you prefer to have shading or no shading within the plot. So now we have analyzed two DSC data files, one using a linear baseline and the second using a sigmoidal baseline, together with looking at how to perform a partial area analysis. Let's now open a DSC data file in which we can analyze a glass transition. Here we have a DSC data file of PET that has been quench cooled from its melt. I can observe that there is a glass transition, cold crystallization peak, followed by a melt peak. Let's zoom into the area of the glass transition. To perform the analysis, I can highlight the plot, right-click, select Analyze and Gloss Transition, or I can select from the Analysis tab on the menu bar and then the pull-down menu, Gloss Transition. By selecting the Settings option, under the Pre-Start Status, I can observe the types of options being used for the analysis. The midpoint type is currently set to half height, but can be changed to inflection, half height, half width, half extrapolated tangent. The onset type and set type can also be edited from tangent to manual tangent, and the transition type can be edited from tangent, manual tangent to inflection. For further information regarding the differences between these options, select View, Help, and from the Help window, select Analyzing Data, Available Analysis Functions, Gloss Transition, and in here you will find detailed explanations regarding the differences between inflection, half height, half width, half extrapolated tangents, and fictive temperature, as well as tangent and manual tangent. For this analysis, I will perform a half height analysis. Select Analysis, Set Limits, and move the DSC analysis crosshairs to the appropriate temperature range. You can also select from the Settings window under Status, Select Limits, manually enter the temperature range for the analysis. Right-click and then select Accept Limits. What is currently being displayed is the gloss transition midpoint at half height. Additional labels can be put on this plot, which include analysis, midpoint type, onset, as well as endset. Further adjustments to the appearance of the plot can be made from this window as well. So now we have successfully analyzed the gloss transition of a material, and we now have data and analysis for 3 data files. Let's move on to saving these 3 data files as a saved session so that they can be reopened without having to redo the analysis. To save a session of analyzed DSC data files, also known as a results file list, highlight the 3 data files within the File Manager window, right-click, and then select Results File Lists, and then Save. Note that it will now have a TRFL extension, which stands for Trios Results File List. And it's currently being stored to a preset directory under the C folder, Documents, All Users, Application Data, TA Instruments, Trios, and then Data. This directory can be changed and edited to a directory that you would prefer. Under File Name, type in the name of the session that you would like to have it called, and then select Save. And that's how you save a session of analyzed data files within Trios. Now that you've analyzed your DSC data files, let's look at exporting these plots into Microsoft PowerPoint, PDF, and other graphic format files. To export to PDF, please select the TA bubble, select Print, and then Print PDF, or select Save As, and then select Save PDF. And from here it would be stored to a default directory within the Trios data folder. And then type in the name of the data file and select Save. By doing this, it automatically launches the ET PDF document in which you can see the data file title, onset, endset, midpoint, analysis, and then the plot. You can also right-click on the plot, select Copy, open a program such as Paint, select Edit, and then Paste. You can now save this file as a JPEG, bitmap, or any other graphic format. Within Microsoft PowerPoint, you can insert that saved picture file by selecting Insert Picture, browsing to the location of that data file or picture file, and then selecting Insert. The plot can be resized as needed. So now we've gone through a couple different options of exporting your plot into a format that can be used for your results analysis options. Thank you for joining me in this Discovery DSC Data Analysis Using Trios eTraining course. Within this course, we covered topics which included opening a data file in Trios, reviewing the parameters and graph properties, analyzing transitions, specifically the gloss transition and peak integration, overlaying multiple plots, and saving a Trios session file, and then exporting plots to programs such as Microsoft Excel, PowerPoint, and PDF. If you still have questions regarding data analysis within Trios, please do not hesitate to contact us at the TA Instruments Applications Hotline by email or telephone. We're looking forward to hearing from you as we want you to become familiar with the operation and analysis of your Discovery DSC.